So the book has a whole chapter on dimensional analysis that I think is a little bit too long. I'm going to present it. I'm going to give you sort of a mini pamphlet. It's going to involve a little writing today, but you'll find it'll be, I think, more concise than the book. Typical lectures won't be like this. Most of it we're going to be doing problems. We're going to be a little formal today. So this quiz is going to be on dimensional analysis. And so basically each problem, as I'll show you in the quiz, is basically you're trying to figure out what the dimensions that govern the system are. And like we saw in that the problem, sort of the article I put on the board previously, when you use dimensionless groups, you can minimize the number of parameters governing the system. Like if you listen all those parameters I had, like the thickness of the bubble, the radius of the bubble, the viscosity, the surface tension, the density, those are like 7 variables. But those graphs, they fit all that data on just 2 graphs. So they basically figure out these new variables that are like a weird like product and ratio of those. Okay. So in that sense, it minimizes the number of parameters governing a system. The physics doesn't depend on each one of those per se, but basically on the ratio. And occasionally it yields what we call a scaling, basically an interdependence. Interdependence. So for example, that graph, it was plotting the dimensionless thickness of the bubble or the number of wrinkles as a function of these other parameters. And you saw those sort of lines. Those are dependencies. Those are things that you can solve out of the governing. Now, for every quiz, there's going to be, the reason I divided up the fluid mechanics into seven areas, because I really just want you to focus on a single sort of idea. And the only idea we have in this quiz is what's called Buckingham's theorem. I don't think that's the same dude that was Buckingham's palace, because that was way longer, but it's this other English fluid dynamicist named Buckingham. Let's just write it down. This is worth writing down. I think it's really the only way to get into your head. Here's some. Buckingham's theorem. So Buckingham, like you have that bubble bursting problem. You've got all these physical variables that you could potentially change to look at how many wrinkles you have when that bubble bursts. You've got the density of fluid, viscosity, the surface tension, the size, physical size of the bubble. You know, lava would have a way higher density than some other material. So this close to my mouth, and maybe they can hear me better. That's not as close to you guys. So you've got all those physical variables governing it. But Buckingham said, hey, you don't have like 10 physical variables. What you have actually is instead maybe 7 different, n minus n different pi groups. The pi groups are the dimensionless numbers that we're going to try. And what determines the number of pi groups, the number of dimensionless groups that we want to find, are the number of fundamental units. And then you get n minus. And of course, we're going to have to do an example because this is totally abstract right now. But that's really all this quiz is about. It's about figuring out how many dimensionless groups you have and making sure you can figure out the time progression. All right, now I got to change course. See if Luty's world has any. We can't see you. Like someone is fine. They want to see me? Adjust the ratio of the screen to slide and blah, blah, blah. They seem like they're fine. Simon, is your friend fine? All right. Come on, kids. All right, rear camera, cameras, or 2. All right. So we just use this pi notation to refer to groups of. Yeah. It's n minus n. There should be two things: n independent dimensionless groups, and m and n. And this is n minus n.
Okay. What's like the bottom line?
Oh, that's n minus n too. Sorry. My squat position, my handwriting. All right. So the new information here, you got to figure out what the heck these fundamental units are, these physical quantities. I'm going to tell you. Okay. So we got to figure out what these independent physical quantities are. And the key word is this word independent, which you haven't seen used before in a fluid mechanics context. So the following are independent. These are the ones that you're going to be using probably most often. Mass, length, and time. If I've got a 10 kilogram weight, I can't tell you how heavy that is just by using meters or time. You know, the weight's going to just be that weight. Similarly for the other units. Now these following would be dependent. length, time, and velocity. Take the example, if any of you are commuters. Anyone commute here? You commuted?
I just had a question.
Oh, yeah.
Length, independent, and dependent.
When I say dependent is, I mean this set of three are independent.
Okay.
This set of three variables are independent. So basically, give me a couple variables, I'll tell you if they're independent or not. Those are independent. When I look at this new set that has length, time, and velocity, those are dependent. Because, anyone commute today? Where'd you come from?
Norcross.
Oh, Norcross? What about you in the back?
Newton.
Newton. So basically, you know, this average speed that you're on the highway is the distance from Newton to here divided by the time that it took you to get there. So these three things are dependent. In particular, U is dependent on L and C. So you wouldn't, for example, if you were to choose basically independent variables, you wouldn't be able to choose this set. These are not independent. So they're not, the velocity depends on the speed. The velocity depends on the length, the duration, and so the whole reason why we have Booking's theorem in the first place is because it's a fundamental idea. It's the basic idea behind the law. You know, this law is kind of couched in a number of variables, and etc. If you told someone on the street, it wouldn't make very much sense. But you can tell this to someone on the street that basically physical laws, like Newton's law, Navier-Stokes law, Pascal's law, which we'll all derive in the course of the class, they must be independent of the units of dimension. No one says Newton's law. Oh, Newton's law in like meters. No one says that. And that's because, as I was saying, like all units that we come up with are arbitrary. Like, didn't you hear the story, like, the width of the road is equal to, like, 2 horses' butts? Because, like, originally we didn't have roads, we had the horses, and they went down these paths, and they had to make sure that the tunnel was wide enough for 2 horses. But basically, those are all just arbitrary. They just happen because of history. Arbitrarily chosen. So, units are arbitrary, and physical laws don't depend on them. And we got a couple different units that you'll probably use when you do the homework. One of those is called, does anyone remember what SI stands for? Yeah, standard international. Meters, kilograms, seconds. If you want to work on small scale things like I do, you do centimeters, grams. I think the US and maybe one other country uses feet still. What's the other country that uses feet?
US, Liberia, Myanmar.
Liberia and Myanmar. It all works. Okay, because they're independent of dimensions, therefore, the behavior of a physical system is okay. So basically, if you want to describe physics, you can't just look at the units of something. You have to look at these things called the dimensions. And we just denote them by pi sub I. The I just means that we're going to have several of them. But they're going to be more meaningful than the pi is just sort of a dummy symbol. You guys need more time with that. So the next thing, I'm going to give you a step-by-step process that uses Buckingham's theorem to figure out how many groups you have and what they are. The book spends a large amount of time using this method of arbitrary exponents, and I think it's really belaboring the point. So, but some of you may prefer that method better. You guys all set with board 2? They're quiet. All right. So there's one corollary, right, that basically allows Buckingham's theorem to be useful. So one of the reasons we use Buckingham's theorem is because we want to figure out how some dimension groups depend on others. The most famous dimensionless group is probably refers to drag, how much drag you have on an object. Do people know about using those, those wind tunnels, and you put this tiny little airplane into the wind tunnel? Does anyone know why the heck anyone wants to do that? Just see lift. But why would anyone know the lift on this tiny little object? Yeah, it's because if you discover the physics on this object and you know the relationships between the dimensionless groups, you can calculate the drag on the bigger object. And they didn't figure out this until Buckingham and Reynolds figured out this idea of like how much inertia a turbulent. But if you talk to someone on the street that you can actually measure this little airplane and actually scale up this really big airplane, it's pretty unbelievable idea. So there's kind of two cases that you're going to encounter in the homework and quizzes. One is that there's basically a more than one dimensionless group. Okay? So if n minus 1 is equal to p, then you can express one group as a function. You can express the drag as a function of other groups. M minus n. I think I don't know what I said, but that's supposed to be it. This is going to be what's going to happen most typically in the quiz. That you're going to get so many variables, you can get like 10 variables, just like I showed you in the science magazine. You can get like 8 dimensionless groups, and you're going to have several dependents. Before quiz day, I'll give you this one problem that has 5 dimensionless groups, and if you can solve that problem like in a reasonable amount of time, you should be pretty good for the quiz. And so, like I said, this would be a useful way to think about this. This would be the drag, which is a function of, the size, the ratio of the width of the airplane to the height of the airplane. How much viscosity is, which we'll talk about. This is going to appear in this group called the Reynolds number, which is the most famous. So there's a special case that we'll pretty much look at today and next lecture because I think it's the easiest to understand. It's when you're lucky enough that you have just one dimensionless group. 1 plus 2. So this is where dimensional analysis actually gets in the world of physics. It tells you that if you got only one group, then that group has to be a constant that depends on how you measure it from your experiment. Now here's the 3-step method for obtaining dimensional. The book gives a 7-step method that's 2 pages. Some of you might prefer that. And to be honest, on the quiz day, I think this will become just so natural that you're not going to have to think about it. You really have to reach these steps. And so the other reason, so if you talk to the other 33, 40 sections, they're not going to do dimension analysis first. But I put it first because I think that's the easiest part of the course. I know it's a little abstract right now, but it doesn't involve any calculus. You don't have to take any derivatives. All you have to do is algebra. Like basically, figure out how many terms you have and make sure you account for all of them. So I really want people to do well on this quiz to start their semester off right. So you just have to be organized. So make a list of all the physical variables in the problem, and there's going to be m of them, m as in m and m's, and their fundamental units. Like I said, it'll be mass, length, or time as a fundamental unit. And we're going to have n as in Nancy, that's such a name, of those. Love this thing. I can just use the whole. That's number 1. Number 2, use Buckingham's theorem. You can't use Buckingham's theorem until you know how many units you have and how many physical variables. To determine the number of groups, they'll tell you when you're done with the problem and when you'll be done with the quiz. The Buckingham theorem only comes in once you're organized and you list your variables and the dimensions they have. For example, if I were to list velocity as one of my variables, it would have dimensions of length and time. All right, we've got one more. I'm just going to start writing here. You student need board 2? Anyone? So like I mentioned, 3-step process. The third step is you form the n-n dimensional groups. You're going to get 2 groups, 3 groups. Like I said, I'll give you the one problem that has like 5 dimensionless groups, and that'll be sort of your big test before the quiz. And you do it by this method of arbitrary exponents. That's probably the slowest method that you'll use. As I'll show you, you can do a few tricks along the way that can reduce your use of the arbitrary exponent method. The exponents method is laborious, but sometimes you just have to do it because you have no other choice. And you have to make sure that each one of your friends that you introduced, the n physical variables appear somewhere. Otherwise, you're solving a different problem and you'll have missed something. Unless you have a really good reason for it to not appear. And we'll go over a case where that occurs. And so these dimensionless groups, they're not just arbitrary. They stick with you for pretty much the whole course. We'll derive them when we derive these things called governing equations. So Newton's law, F equals ma, is very simple for solids, but for fluids, the problem is there's a pressure. So there's this thing called Navier-Stokes Equations. And Navier-Stokes Equations has 5 different terms, but usually there's only 2 terms depending on how big one of the dimensions. You can greatly reduce the simplicity of your system if you look at special regimes, like really, really fast flows or really, really slow flows. All right, let's do our first example. And I apologize that it's 8:50. It took me 50 minutes to get to the first example. I believe it is where you learn the examples, but you really have to, know these definitions first. All right. First thing you do with any problem in this class is try to draw a picture. Because the picture will tell you if you missed anything really important. You don't want to do it in your head. Trigo is the frequency of oscillation of a pendulum. Does anyone remember who did this problem first? He was persecuted by, I think he was persecuted by the church for showing that the Earth goes around the sun, where everyone thought that, because man is like the big thing, everything around the Earth. Who? Yeah, I think Galileo did this. Galileo was bored at church one day, and he was like looking up at the ceiling, and he noticed the chandelier was swaying with the wind. And the other thing he noticed is this chandelier seemed to have like a fixed frequency. It basically swayed the same period, independent of, the amplitude. Small sways were slow, big sways were faster, but the period of the sway didn't change with the amplitude. Galileo. One of many scientists to be persecuted by the government. Luckily, he didn't have to die for it. So the whole reason pendulums sway is because of gravity. If you go to the International Space Station with a pendulum or Newton's cradle, and you go like this, nothing exciting is going to happen. It's just going to stay there. Pendulums basically want to fall to their lowest energy point, which is the bottom here. And when they do that, the problem is they gain kinetic energy, and that helps them go all the way to the other point. For example, I would say, analogously, you are at the beginning of the semester, we have all this potential energy. By mid-semester, you're going to be so tired and drained that it is just inertia that is carrying you through until the last day of class where you basically can barely see, but you're just going to get through the other side. So in this problem, we've written 4 variables. We expect the frequency. So this is what experimentalists do. You set up a single variable, frequency, and you want to figure out how it varies with these other problems. Like if you're Galileo, you're like, hey, if it was a glass chandelier or an iron chandelier, what would be the big deal? If I were on Pluto versus Earth, how would it change? If we're 10 meters tall versus a meter tall, how would things change? Maybe people have seen that experiment where, does anyone know the name of that big pendulum that only goes around like once per day? It has a name. Foucault's pendulum?
Something like that.
Yeah. It's like 10 meters tall, so only the biggest science museums can have them. And it swings like once per day. And so basically they put 365 little pegs around it. Basically it knocks down all those pegs. And I think that was one of the first ways to figure out that the Earth actually precesses around its axis because it actually changes its position. So eventually it knocks down all the pegs around its circumference. So big pendulums swing slowly, small pendulums swing quickly. Why is that? Now, maybe some of you remember going to the House of Pain and doing this problem in your physics course. To do this problem, you had to set up a torque balance, maybe F equals ma, or I alpha double dot equals something. There has to be a sine theta because it depends on the height of this thing in the gravitational field. Nice thing about dimensionless groups, you don't have to do any of that. The physics of this problem that tells you how much this pendulum produces is completely in the dimensions. You don't have to do any calculus. So that's what we're going to do. We're going to apply the method of obtaining dimensionless. All right, I got to go more here. The pendulum problem is a very, very deep problem. It's like, it appears so much in biomechanics and other subjects. For example, it dictates why insects have 6 legs. When you basically are smaller than a certain size, you don't have enough time to stop yourself from falling. Like if I stand on one leg, it takes me a second to fall. But if my leg were a centimeter tall, it would take like a millisecond. And no insect has a reaction time fast enough to sort of stop themselves from falling. They've got to have like a stable tripod. This fundamental frequency that we're going to drive basically dictates a whole lot of the reason why we have 2 legs and not 6 legs, and why there's no really big insects. Step 1. So I'm going to do this a little pedantically just so you get it the first time. We list the physical variables. And I guarantee you, there's going to be at least 2 or 3 people on the quiz that do this first step wrong, and they get the whole problem wrong. You don't want to rush. If you rush, you'll get there slower. So let's list them. The frequency of the pendulum, the mass of the pendulum, and gravity. So, unfortunately, this is terrible notation, but that m on the top is mass, and this m here is the number of variables. How many variables do we have? Everyone just shout it out. One more time.
4.
Yeah. I guess when you shout wearing masks, it's just always kind of. All right, 4 variables. Do not get that wrong. If you get it wrong, you're going to either miss a variable or you'll spend too much time figuring out a variable that doesn't exist. I mean, a group. Okay, that's the easy one because I have given it to you. And in the quiz, I will give you all the variables. You won't have to guess. In real life, no one's going to hold your hand. You're going to have to figure out what the variables are yourself. But on the quiz, I'll give them to you. I think those of you that are going to be professional scientists, you should think about how in the world am I going to figure out these variables? All right, next. Those variables are couched in certain units. What units are used to make those variables? So I'll just write the units of each of these things. What's the units of omega, frequency?
Hertz.
Yeah, hertz. Or 1 over time. The mass is mass is mass, length is length. Gravitational acceleration. Who knows the units of gravitational acceleration? Say that again.
Is it mass per time squared?
Mass per time squared. Close. Length. Good. Got the time squared right. That's actually a tough one. Like, a lot of people don't remember the units of gravity or acceleration. And I always forget these two because my memory is just terrible. The way you remember that units is you remember the following equations: F equals ma. Okay? I guess that's the way you can do it. And so this is mass length over time squared, and this is a mass length over time squared. Or you think, you try to memorize certain formulas like the distance is equal to 1/2 gt squared. So the distance something falls is the time squared, and then there's you got a g. The only way you can get a distance out of a time is you multiply by length per time squared. So you try to come up with formulas that help you remember it. I will also give you the units of this on the quiz, just because I'm nice sometimes. All right, so mass, length, time. I used to not give the units. All right, so all of those things that you had in common, we have the time, mass, length, and you notice a couple of things. First, I don't try to use the word seconds because you could have other arbitrary units of time like hours. So we just call it time. So basic math, length, and time, those are the 3 units that describe all the variables that are given. And so how many of those we have? We have, of course, 3. So we got m is equal to 4 and n is equal to 3. That was step 1. A very important step because that sets the stage for your next step. Buckingham's theorem. I don't even give this on the cheat sheet for the quiz. I give you sort of formulas that you need. For this quiz, I think everyone can remember n minus n is equal to the number. So basically, you get one dimension. So you get one dimensionless. So Buckingham's theorem tells you how many steps you have to go to figure out the dimensionless group that characterizes this system. And in turn, that's going to tell us how frequency depends on length and mass. And it will in a second. You just have to trust me for now. All right, this next one I'm going to do. All right. Now the method of arbitrary exponents. I'm going to do it once for you. We'll do it a few times actually. Basically, it sets up a mathematical problem that wants to figure out, what kind of product of these variables that gives you something dimensional. And I'm going to introduce. So I had 3 friends in my party: frequency, length, gravity, and mass. And I'm going to invite 3 new friends that I'm going to have to figure out who they are. They're these arbitrary exponents. They're going to be numbers like integers, fractions. But I'm trying to figure out what combination of these cancels out all the units. In the end, I don't want pi to have any units. So I'm going to figure out the numbers that are A, B, and C, and this is the way I set it up. There's a couple subtleties here. One, omega has no exponent on the top. And the reason for that is because I want to figure out how omega depends on these. That was the whole point of the problem. The whole point of the physical problem was, you people in the Boolean world kind of hate me because I'm on this side. But I'm trying to figure out what the frequency of oscillation of the pendulum. So I need frequency to be in the end. I can't constrain it so that it doesn't appear. So that would be kind of like self-defeating. So I know frequency is going to have to appear, but I don't know how many of these. If I have 3 of these, 4 of these, 5 of these, who knows? And the way I set this problem up, this is how I try to find out, how this works. So up above, I've already written the units of each of these things. I put in this bracket symbol. I'll make it even a little cleaner. So those are the units of each of those variables. And the next step is solving for A, B, and C. It no longer matters what the names of these funny things were. They could have been some weird name like alpha, beta, gamma, whatever. The only thing that matters is how many of these depend on is what their units are. So I'm going to replace them with their units. And I'm going to use this symbol. So this means units of x. Bracket, square bracket means units of x. So the units of pi, I'm going to substitute. I got 1 over time. I got length scaled to the a, length over t to the 2b, b, and m to the c. Where all I've done is see all the units up there, I've just substituted them down here. And you might have to review, but you take a fraction to the b, it means the numerator and the denominator both go to the b power. I would say this is also a trouble place where people kind of mess up, that they don't know their basic algebra from high school. All right. Okay. So this is a new equation that tells me what this is, and I want this on the left-hand side to be 0. So what this is actually 3 equations. It tells me how many t's I need, how many m's I need, and how many l's I need. So, for example, if I solve for t, this is what I'm going to get. I get 0 because this is the number of times. I want the times to cancel out, so I'm going to put 0 on the left. And in the beginning, I got negative 1 times, and then I got minus 2b. In other words, there's a relationship between b and this thing, so that basically cancels out. And that's the only possible relationship, so that you get no t's in the end. You don't have much choices with the t. L is 0 is equal to and m. See if you can do this at your seats. And then some of you that are pretty far ahead, try to solve for A, B, and C. So I'm just physically counting how many t's, m's, and l's I get. Do that while I erase. So you count the occurrence. It's a product. Count the occurrence of t's, l's, and m's and make sure they all cancel out. And keeping in mind they're independent. The number of t's doesn't affect the number of l's, nor does it affect the number of m's. Those are all independent equations. All right. So the number of l's, we had a plus b. The number of m's, we only had c. So you solve for this. First, you find out that c is equal to 0. That means c can't appear in the equation. A is equal to 1/2, and b is equal to negative 1/2. Okay. And so this is basically what we are looking for. How many a's, b's, and c's we get? And we get this final expression, pi is equal to omega. This is my dimensionless group. That was the whole sort of point of doing the problem. I figure out the interrelationship between these variables so that this new product is dimensionless. And by Buckingham's theorem, phi is a constant. Oh, yeah, thanks. Phi is equal to constant. So, as a constant, I'll call that the variable c. That means omega is equal to L algebra. So this scales as simple means quality up to a constant. A scales B. Okay. So it says that the frequency of pendulum only depends on the length. So physically, this tells me that in the end, this is probably the one that you want. It says that basically, if I wanted to have pendulums that swung, half as much, I'm going to have to increase the length of the pendulum by a factor of 4. Yeah. Yeah.
Is that the C all for?
No, it's a different C.
Okay. That's equal to 1 and minus B?
It's just an arbitrary constant. Okay. I'll call it D.
In the next line.
Maybe. It doesn't really matter, but this is like an arbitrary constant. Well, it just means there's some constant that I've got to figure out, and I figured that out. So how do I get D? It's deduced from experiment. Single experiment. So if you're going to do this like with Galileo, he would actually, measure the height of the chandelier. He knows the constant of gravity, as Newton figured out. And then they basically figure out how these relate, and then they calculate this arbitrary constant D, which depends on like friction and drag, I think. So a couple things. Omega doesn't depend on the mass of the pendulum. So some of you might know that. Like I think Galileo, he also showed that you drop two objects of different weights, like a feather and something else. As long as you put them in zero, no drag, they're going to fall the same. They're going to accelerate the same amount. Similarly, that chandelier going into the glass with some other material, the gravitational energy is going to always equal the kinetic energy, so the mass is actually just. Some of you might know this as what's called the natural frequency. Basically, depending on how tall the object is, it tells you just basically how quickly it's going to swing. I think that's it. So next time we're going to do this problem of the atomic bomb. So example 2. Next class. There's this famous scientist, fluid dynamicist called G.I. Taylor. In the 1950s, he was the first to witness this atomic bomb explosion that was filmed, I think in New Mexico somewhere when the U.S. was testing. And they published these photos in Time Life magazine. And he was able to, based on the photos, to determine how much energy the atomic bomb had. It was like 10 to the 20 ergs, so something huge. And he did it all through dimensional analysis by looking at the rate that this bomb is sort of just the sort of mushroom clouds spreading over time, and the density of air and other such variables. But he was so close that the CIA actually came to his house and and they accused him of being like a spy. So he got these photos from Time Life magazine. We'll do this problem next time. There's also a case of a single dimensionless group. And I hope you see the power of dimensional analysis. You can get some physics without having to do any physics, just by looking at how many dimensions each of these things has. I will upload I'll upload the homework solutions soon, and I'll soon upload the quiz from last year, so you can look at it. But it's basically going to do 2 problems like this over a period of 1 hour and 15 minutes, which is absolutely plenty for this quiz. The other quiz will be not absolutely plenty. So this quiz should be pretty easy.